let's take a look at what an ideal low-pass filter. Its DTFT would be purely real. If it was ideal, if you could have anything you wanted, it wouldn't muck around with the phase at all, and it would be exactly equal to 1 for discrete frequencies between, say, 0 to pi over 4, if it was a pi over 4 cutoff, and 0 for pi over 4 is less than or equal to omega is less than pi radians per second.
Sir,
So
what is the, what is the subscript for the H?
Low pass, LP. So if we were to graph that, H low pass of e to the j omega, so we're graphing here the DTFT, it would look like passing low frequencies, the value of 1, and then instantly stopping right here. And depending upon your sampling frequency, that would correspond to, say, a low-pass filter that would pass all frequencies exactly less than, say, 500 hertz, and then at 501 hertz, it would instantly stop it up to its highest frequency, which was 1,000 hertz. And by the way, if it was 1,000 hertz, that was its highest frequency, you know its sampling frequency had to be twice that, or 2 kilohertz. Now, because we're in the discrete time domain, let's go back to discrete time thoughts. We know it's got to have certain symmetries here on ad infinitum. And so typically we just graph this section, although just because we only graph that section doesn't mean that the rest of it doesn't exist. You'll notice I was tricky. I only defined it over that region. If I tried to define it over all omega, it would have to be some sort of odd infinite summation of this thing, which would look very complicated. What is its impulse response that can give us this magic, perfect low-pass filter? From the integral I talked about last class, you can invert a capital H, a DTFT, back into the time domain by using this formula. And I'm going to go through this derivation one time, just so you see how to actually do the math here. So if we're going to integrate between negative pi and pi, we're going to be multiplying over here by 0 in this region. So it's really only particularly we only need to integrate between negative pi over 4 and positive pi over 4. That's the only region where we're not multiplying by 0. And here we're multiplying by 1, so this goes to 1 and it just goes away. And now we can do the integral. And despite the fact that we're integrating a complex exponential, so it has real parts and imaginary parts, it works the same way as if it were as any other kind of exponential. Since we're integrating with respect to omega, we use the chain rule and we take out the integral of this with respect to omega. So that would be 1 over j n e to the j omega n, evaluated between negative pi over 4 and pi over 4. This is just calculus. The next step is just calculus. These are all constants, so they come out, and we get a to the j pi over 4n minus e to the minus j pi over 4n. So at this point, you go back to those Euler's relationships. I'll write them all very quickly. E to the j theta, it has a real part, which is cosine, and it has an imaginary part, which is sine. And that means that we can, with a little bit of algebra, we can solve for cosine and say it's equal to the sum of two complex exponentials. We can similarly solve for sine, which is the difference of two complex exponentials, but with that j in the bottom. So when we look at this thing, we want to use Euler's relationships to simplify this. We can see it's got this j in the bottom and this minus. So we're going to try to make it look like this somehow. So we can pull out our 1 over pi n, and then we're left with 1 over j2. So that looks pretty good. Of e to the j pi over 4n minus e to the minus j pi over 4n. And I pulled out that 1 over pi n just to make it look exactly like the rest of it look exactly like this. And now we can just observe that this is our theta. And so we can convert that into 1 over pi n times sine of pi over 4 times n. So this is our exact impulse response of our perfect low pass filter that has an infinitely sharp transition band. That's pretty crazy. Now, of course, this, if we were to graph it, it's sadly infinite, and we'll have to somehow limit that. If we were to make this thing n continuous, it would have that sine component going down with an envelope that goes down as 1 over n, so that sine would slowly dampen out. And so since we're in discrete domain, we'll get something that looks like this. And now you can make your filter look as accurate, have as steep a slope as you want, just by including more and more samples of it. This is crazy what you've just done. This is taking the idea of a low-pass filter that you learned about in continuous time, but now you actually know how to make an honest-to-God one. You could program this into MATLAB and make it accurate for, say, 300 samples. After 300 samples, this 1 over n part is going to get really small. Your inverse will look extraordinarily close to this. And then if you wanted to start looking over data that has tiny little signals buried in it, again, stock market data, data from astrophysics, looking at how the light from a star slightly dims on a regular basis when a planet goes in front of it. You can do this in a way that would be completely impossible to do in continuous time.
Sir, the graph you have in the top right, is that the input that goes into the low pass filter initially?
No, what we're graphing here is an x of n that goes into our system, and this system happens to be a low pass filter. And then what we get out of it is our y of n. So here we're not talking about a particular input or a particular output. We're only talking about our system. This down here is our h of n, and what's in the upper right is if we move this over, DTFT, into the frequency domain, this would be our input in the frequency domain. This would be our system transfer function, our DTFT, in the frequency domain. And what we would get out would be just the product of our input with our system transfer function. Does that answer your question for us?
Yes, sir. Thank you.
Sure. So we're just talking about the verb here, the things that changes our signals, and then you can plug into it whatever you want. This, by the way, is also the way that the filters would be designed in any kind of music listening system, because now you can change your filter and make it more bass heavy, less bass heavy, dynamically. Just simply recompute the new h of n, plug it into your filter, and then inside your MP3 player, there's a convolutional operator that's continuously convolving this with your input x of n to give you your output that you're listening to. It's doing it in real time.